Hello, hello, hello. This is the second part of section 2.1, continuing our talk on the distributions of quantitative data. So we talked about percentiles last time. We're going to get into z-scores today and Chebyshev's theorem, and also empirical rule. We'll talk about what those things are. But our ultimate goal for today is to be able to find a z-score for a data value. So just as a review here, um, in our first unit, we did find 5-number summary, which helped us show the distribution of quantitative data with a box plot. Yesterday, we talked about another way you can see like data in an ordered set. That was percentile and percentile rank when we're dealing with um, where you are located compared to everyone around you. And then also z-score is what we're going to get to today. So what is z-score? Z-score really deals with standard deviation. So, what is a z-score? Let's get into this right away. What is a z-score? So, a z-score is basically the number of standard deviations away from the mean. So, whatever value you're looking at, whatever your value is, however many standard deviations away from the mean is, that's going to be found in your z-score. And there's a way to find it. One note: always round to the nearest hundredths. So that is 2 decimal places after the decimal. So 2 places after the decimal. So the formula. So you're going to generally see this formula given for z-score in one of 2 ways. So your z-score in this case is going to be equal to your x value minus the mean and divided by the standard deviation. Okay? So you're going to need to know the mean. You're going to have to know the standard deviation in order to figure this out. Now that is for a sample data. For a population data, your z-score would be the x value minus mu, so your population data, and then divided by sigma, which is your population standard deviation. All right? Now, how will this be used? Okay, so let's just say in Wisconsin, the average ACT score is 20.1 with a standard deviation of 5.5. So let's pick somebody. Let's just say Mike. All right, you got this guy named Mike. Mike scored a 28 on the ACT. Find his z-score. We have enough information to find the z-score in this case. If we look back at that formula, we're going to use the formula of your x value, which in this case is 28, minus the mean, which is 20.1, and divide it by the standard deviation of 5.5. That will get you the standard deviation. Now in this case, that equals, I believe it's 1.39, which means his score is 1.39 standard deviations above the mean. So I'm going to show you that right here. Let's take that information and how we interpret it. So if we have that number, this is how I would interpret it. Blank score, whatever it is z, and I want to make a note here. We use the absolute value when we say it, because sometimes you'll get a negative. But that just means that if it was negative 1.39, that means it's below the mean. So we're going to say this many standard deviations, either above or below. Above will be a positive before you do the absolute value, a positive z-score, and below will be a negative z-score. The only thing I want to really stress is you should not use the word away. Do not say away, standard deviations away. We know enough information that it's going to be above or below, meaning the mean is a certain number. In this case, it was 20.1. His is, on average, like his score would be 1.39 standard deviations above the mean. And this could be the mean ACT score in Wisconsin. So I'm gonna write it out exactly how I just said it, and as a visual for what's expected. And boom, magically there it is. Brian's ACT score is 1.39 standard deviations above the mean ACT in Wisconsin. And we'll talk in just a little bit about what the significance of that is. But let's try one more. Let's take our data here with candy bars. I really need to make this smaller so that we can do more stuff with it. That really threw everything off here. Hold on a second. Sorry about that. So here's our data about candy bars. Find the z-scores of grams of fat for both the Symphony and Baby Ruth bars. So I have those highlighted there. We're going to deal in grams of fat. So what you're going to have to do with grams of fat is go on your calculator, plug all these in, and figure out what the mean and the standard deviation is. Or, boom, I already did it for you. So here's that information. In order to find the z-score for each of them, let's do Symphony first. We'll do that over on the left here. The z-score for Symphony, we'll say, is, again, your value, which in this case is 13 grams, minus the mean we have of 12.37, and divided by the standard deviation of 2.133. That's how I find my z-score. Okay, and you can do that the same thing with the Baby Ruth bar as well. So what I got for a value for that is 0.30. Now why don't you try the second one? Go ahead and pause and try. Baby Ruth, go. All right, I got 0.076. Hopefully you got the same thing. It makes sense that it's bigger because it's a bigger number farther away from the mean. So both of them are less than one standard deviation from the mean, but how you could interpret that for either one of those, let's just say Baby Ruth, you could say the grams of fat for a Baby Ruth bar is 0.76 standard deviations away from the mean grams of fat in candy bars, in common candy bars. All right? All right. Next example. Jack and James are both applying for national scholarship. Jack scored a 23 on the ACT. James scored a 1200 on the SAT. So I may have talked to you about this with my own and comparing to others. ACT and SAT are scored differently. So the selection will be based on this test alone. Who will they pick and why? One of the things you can look at is percentile. All right. I showed you percentile with when we talked about percentiles. But now we want to look at z-scores. Okay. So we have the scores. So think about what information you need. You need the mean and the standard deviation. So the mean, in this case, of ACT, and this is nationwide now. I don't know which year I found this from, but the mean is going to be 21, and the standard deviation, or sigma, is 5.6, whereas for the SAT, the mean is 1100, and the standard deviation is 150. So what you can do is you can individually find the standard, how far away from they are from the mean, comparing z-scores. Z-scores are kind of normed or or standardized, so we can actually compare them, kind of like percentiles. So in this case, we're going to do our little work here. He scored 23, so 23 minus 21 divided by that 5.6. His z-score for Jack, and we're going to say Jack, yeah, is equal to 0.36. Not bad. That's very close to the mean. But obviously, you'd want to be farther away from the mean to stand out if you're talking about test scores, right? So let's compare his. So James was at a 1200. Average is 1100. One more there. And standard deviation is 150. So James' z-score is, that's 0.67. So it is higher. It stands out more. And it's still not like super far away from the mean, but it stands out more according to z-scores than Jack would. Okay? So we can use z-scores in this case, and I would maybe pick James. Based on z-scores, James would be picked. be picked. Now, if this was an FRQ, I would say you should definitely explain this. And this is a good explanation, but you always should have numbers. So z-score 0.67 versus 0.36. So like percentiles, z-score is another way to be able to compare values of things that maybe aren't comparable otherwise. All right, just a couple quick questions, a couple things to note about z-scores. So if your z-score is positive, where are you? Above. We said that before, above the mean. That means if your z-score is negative, you are below the mean. So it does have value to know if it's negative or positive. If your z-score is 0, where are you? At the mean. You're not above or below it, so you're at the mean. And finally, the bigger the z-score, this is absolute value, by the way. I got those 2 bars around it. So the bigger the z-score, the absolute value of the z-score, the more, we'll say, farther from the mean you are. So the more extreme we're looking for. Farther from the mean. In a moment, we're going to talk about how we can see that compared to like the mean on a different example. So you have a z-score of 3, your score is 70, and the standard deviation is 10. What is the mean? Here's an example of how we can use this a little bit. So the information we have is everything except for the mean. This is just formula based. You know the z-score is 3. 3, so z-score is equal to the mean, or sorry, the value minus the mean divided by the standard deviation, which means if I replace things here, if I plug them in, 3 is the z-score. That should be equal to 70 minus the mean divided by 10. Now solve it. Right? I'm going to multiply both sides by 10 to get this by itself. All right? And then I have 30 is equal to 70 minus the mean. Equal sign there. And I can solve it one of 2 ways, but ultimately I get x equal, or the mean equals 40. So the mean score was 40. 40 whatever it is. So that's one way we can use this formula if we're given certain pieces and we don't know others. And here's one more before I show you a visual of the distributions. So let's say person A has a z-score of 2.5 and a score of 100. Person B has a z-score of -1 and a score of 40. Question here is, can we figure out the standard deviation? Can we figure out the mean? That's 2 pieces of information that are missing. So if we are missing both of those, is it possible to figure them out? Yes, yes it is. Think back to your algebra days. If you have 2 variables missing and you want to find a missing, and you know 2 different pieces of information that you can put them together, we need a system of equations. System of equations. So what I'm going to do is I'm going to create 2 different things. Let's say person A. Bingo, right here. We know person A, the z-score is 2.5. We know the actual score is 100. We don't know the mean. We don't know the standard deviation. Let's take person B. Person B, we know it's -1, and that's going to be a score of 40. This is in the same situation, so they both should have the same mean and the same standard deviation. So what I'm going to do with that now is I'm going to solve my system of equations however I want to. You can always use elimination or substitution. Either way for this, I'm going to get the s off the bottom. So I'm gonna multiply both sides by s here. So I have 2.5 s equals 100 minus x bar. And this one I'm going to multiply by s on both sides as well. So I have negative 1s equals 40 minus x bar. And I'm going to just use elimination because I can kind of line these things up and eliminate one of the variables. So at this point, I'm going to take 2.5 s equals 100 minus x bar. I'm going to line up the other one underneath it, but I'm going to multiply it all by negative 1 first. Why am I going to multiply it all by negative 1? So that I have a positive x bar. So this is going to be s, or 1s, equals negative 40 plus x bar. That way, I like it because I can add these two together. And the x bars cancel out. So I have 60 equals 3.5s, 3.5s. And if I divide both sides by 3.5, I would get s equals 17.14. There's my standard deviation. If I plug that back in for either equation, I can get the x bar to equal 57.14. So now I have my standard deviation and my mean. It might require you once in a while to do that if you're missing two pieces. So what I've been talking about, where does this all fall in what we've been learning with distributions? So I want to talk to you now about Chebyshev's theorem. Yes, this guy's name was Chebyshev's. It's a pretty sweet name. But Chebyshev's theorem pretty much states for all data sets, no matter what it is, no matter what the curve looks like or the distribution looks like, at least 3/4 or 75% of the data will fall within 2 standard deviations of the mean. And at least 8/9 or 89% of the data will fall within 3 standard deviations. It could be more, but at least 89%. So it is unusual to have a score that is more than 3 standard deviations away, which would categorize it as an outlier. Okay, so I'm going to create a little graph here just to visualize that. Let's say my distribution looks like this, not consistent at all, something like that. And we have it on a graph. It doesn't matter what our graph looks like, but here's my graph. There's my distribution. Basically, what that is saying is, let's put your mean right here. And then all of the data, 75% of the data is going to be within 2 standard deviations. So what I'm going to do is I'm going to draw a couple more lines. Let's say this is 1 standard deviation away. This is 2 standard deviations away. And within that, so this is our mean. We'll say our mu. And if you add 2 standard deviations, that's going to be 2 sigma. You get there. If you subtract 2 sigma, you get here. And inside of that, from here to here, should be 75, at least 75% of your data. Now, if you go 1 more standard deviation away, a 3rd standard deviation, okay, that would be taking your mean, your population mean, adding 2 standard deviations, or subtracting 2 standard deviations. You would have up to, or at least, I should say, 89% of your data. Could be more. And anything outside of that, anything in here or in here, those are unusual. Those would be considered outliers. So how we can use Chebyshev's theorem is we can look at an example. Let's just take, I think I have one here. Home prices at Hamilton School District. So home prices in Hamilton School District are skewed to the right. Mean home prices are $250,000 with a standard deviation of $100,000. What would a home value need to be considered unusual or an outlier? So let's take a look. If it's skewed right, I'm visually thinking, okay, Chebyshev's theorem, which I'm going to abbreviate as Cheby's theorem. Basically, we're looking for anything that's, sorry, that was a terrible, no, my pen's not working. Mu plus or minus, if you want to go above or below mu, 3 standard deviations will be outliers. So let's think about that. If your mean is 250,000 and you want to add or subtract 3 standard deviations, that's 3 times 100,000. What happens if you subtract 100,000? So our lower bound. That is a negative 50,000. Now that doesn't make sense. You can't have a negative $50,000 home. Not possible. Right? So we don't even look at the lower bound because nothing is going to be crazy to be less than that. However, the upper bound, if you add 300,000 to that, you'd be at 550,000. So what that means is, if I were to summarize all of that, right here, I would say home prices above $550,000 are considered unusual. I wouldn't necessarily say the word rare, but it's approaching that, are considered unusual. All right? So that's how we can use Chebyshev's theorem. We could do another one here. In first block, the mean test score was 75 with a standard deviation of 5. Find a likely interval for student test scores that would not be considered unusual. I'm going to pause it and have you try this one based on what we just did. So hopefully you tried it, and because we are looking at a distribution that we don't know much about, we're going to use Chebyshev's theorem, where the mean plus or minus 3 of the standard deviation will give us our likely range. Anything outside of that range would be considered unusual. So our likely interval we set up here would be 75 is the mean, plus or minus 3 times 5. So that's the standard deviation. That gives us 60 and 90 as our upper and lower bounds. And what we can conclude from that is that we would expect student test scores to be between 60 and 90 points. At least 89% of them should be between 60 and 90 points. Anything outside of that would be considered unusual and would be an outlier. All right? Now, there is one other way to tell where things are, or if things are outliers or not, depending on the situation. So for data that is basically normal, and I'm going to highlight that, underline that, note that, basically normal, we can be more accurate of where the data is going to fall. Okay? And this is called the empirical rule. So the last part here is the empirical rule. Sounds super awesome. But so does Chebyshev's. In the empirical rule, it states that 68% of the data in a normal distribution will fall within 1 standard deviation of the mean. It has to be a normal distribution, though. 95% of the data will fall within 2 standard deviations of the mean. 99.7% of data will fall within 3 standard deviations of the mean. And I'm going to give you a nice visual here. So this is your normal distribution, your normal curve. And on a normal curve, we're going to say this is our mean, our mu. This is going to be 1 standard deviation away. This is going to be 1 standard deviation away or below to the left. All right. Now, this is going to be 2. Mu plus 2 sigma, and then mu minus 2 sigma. In that first category, 68% should be within 1 standard deviation. That means we've got 34% on each side. In the normal distribution, we can say that within 2 standard deviations, you're going to have 95% of the data, which tells us that really, after that, we only need 2 standard deviations to be an outlier. Because 95% of the data should be within there. Anything outside of that is going to be an outlier. So I'm going to really put in here, these are our outliers. So note, more than 2 standard deviations away would show outliers. But again, we could make another line in there that says, that has all the way up to 99.7% for 3 standard deviations. So really, like, almost all the data is going to be within 3 standard deviations. And that is for a normal distribution that we know is normal. All right, so let's just look at a couple things about that. If you know that's normal, you only need to go 2 standard deviations away from the mean. So we could look at this. You could sketch a curve. We're going to jump around here. I want to highlight what we just talked about. When we are looking for how far things away are, if there are standard deviation, how many standard deviations, if there's any outliers, looking at the shape kind of determines how we're going to decide what we do. So if you know the shape, let's just say yes, you do. Then it depends what the shape is. If it's basically normal, what are we going to use? We're going to use empirical rule. So if it is basically normal, use empirical rule. You know the 68%, the 95%, and the 99.7%, and only 2 standard deviations away. If it's not basically normal, if it's any other shape, what are we going to do? Use Chebyshev's theorem. Which is the 75% within 2 standard deviations, at least 89 within 3. If you don't know the shape, use Chebyshev's theorem. So the only time you can use the empirical rule is if you actually know that it's basically normal. Okay? So, I want to wrap it up here, but just a couple quick examples. Would 100 grand be an outlier? We can look at it. This looks like it's basically normal. We would use empirical rule. Example here. This is definitely not normal. This looks like it's skewed right. So we would use, to determine if it's an outlier, we would use the Chebyshev's theorem. It just depends on that shape. So, closing question to think about, is it always good to have a high z-score? Kind of like, is it always good to have a high percentile? Not necessarily. Think of examples where it would not be good to have a high z-score. And so our goal today, our overall goal was to be able to find z-scores, and then we are also just talking about how we can use it and how we can use it to determine outliers. So that's our lesson 2.1b. We'll see you next time.